Good morning, good afternoon, good evening, whenever you're watching this to study for the unit test on inverse functions. I am working on this, I guess, at 10:45 a.m. on Friday, December 6th. You really don't need to know any of that though, so I'm about to jump into working through some of the practice problems on this series of Check Your Understanding so I can post it on YouTube and use it as a resource to help students study. All right, that's all you need from me. I'm going to turn the video off. And so on this very first set of problems, questions, check your understandings, etc., we have just a question of are these functions inverses? I did make sure each one of the graphs here is a function to start. And a simple way to check if they're inverses is visually, does it pass the test of a reflection across y equals x, right? Um, It does indeed look like it's that reflection, but let's check a few points. And so I have 0, -2, and here we have -2, 0. Here I have the point, what is that, 4, 0, and here's the point 0, 4. Any point that I can find on these two functions will be transposed, meaning the inputs and outputs are switched. That's it. And so because of that, these two functions are in fact inverses. Now let's check to see if this holds true with the second graph. Visually, this looks like it's passing the reflection test. Here's the point 2, comma 1, 2, 3, 4. And so 4, 2 is a point on this graph. Cool. This right here is the point, what, 8, 4? 4, 5, 6. Nope, 7, 4. And so 4, 7, it's reasonable to believe that's 4, 7 there. And I can't really see any other more clear points, but it does look like this y-intercept corresponds to this x-intercept, so I'm inclined to believe that those are two inverse functions. All right, moving over to the medium section over here. If I want to know if they are inverses algebraically, I can go through the same route as what we did graphically, graph them, etc. But I do want to see that we know how to compose them. So remember, for inverse functions, the composition in both directions is equal to x because they are inverses, completely canceling each other out. So f of g of x would have g of x substituted in the place of x, or the square root of x minus 2 squared, which is the square root of x minus 4 squared. Now, the things don't all cancel out, so they're not inverses of each other. What I will point out is that square does not even cancel the square root because we have to subtract before we can square all of that. And so that's as simple as it gets. I don't even have to check the other direction because that did not simplify to just x, so these are not inverses. Now we can check this number 2 here, and I definitely want to work through this one because a lot of people would be inclined to think that these are inverses. And I get the inclination for that. I actually specifically designed this question. Notice there is g of x being substituted in for x. And so when I square negative, it becomes positive, and the square of a square root cancels each other out. So I am left with 3 times, oh, that's supposed to be a 3 down here. 3 times x plus 4 divided by 3 minus 4. 3 divided by 3 is 1 equals x plus 4 minus 4 equals x. And so this is why you actually have to check both directions. That direction, it does look like they are inverses. But if I look here and compose this way where f goes in for g, I'm left with the negative square root of 3x squared minus 4 plus 4 all divided by 3, right? So 3x squared minus 4 is being substituted in for x as that f of x. And so negative 4 plus 4 is 0. Square root of 3x squared divided by 3. 3 divided by 3 is 1. Negative square root of x squared. The square root of a square is, or they cancel out, it creates an exponent of 1, as I'm left with negative x. Notice that is not x, so these are not inverses. Most people would think they are, but that is why they are not. Number 3, a lot of people would actually think that they're not because we see an 8 and not a 2, but this is where it's important, and this is why it's a spicy one. It's important to be attentive to the order of operations. So the cube root of x cubed divided by 8 minus 3 and then plus 3, right? So x cubed divided by 8 minus 3 is being substituted in for x as g of x. Negative 3 plus 3, super simple. That's going to create that 0 there. And then I'm taking the cube root of that whole expression. And so if you remember and think back to when we worked with imaginary numbers and simplifying radicals, there's a special property of radicals that ties into exponents where I can simply split up the radicals, that one radicand, into 2 or 3 or 4 radicands based on the number of factors. And division is a type of multiplication. And so I'm left with 2 times the cube root of x cubed is x divided by the cube root of 8 is 2, right? The idea that 2 cubed is 8. So the cube root of 8 is 2. And so looking like they're inverses right now. Wow, that was terrible English. It is looking like those are inverses right now. G of f of x is equal to 2 cube root of x plus 3. There's g of x, and that is cubed, divided by 8 minus 3. In a similar way, right, I'm going to cube the 2 and cube the cube root. And so the cube and the cube root cancel each other out. And x plus 3 minus 3 is equal to x. Notice those are, in fact, inverse functions. I'm going to have to check, but off the glance, I believe that number 4 is one where students would think that it might be inverses, right? We have a logarithm and an exponential, we have subtraction, we have addition, but be attentive to the order of things. It even looks there like it might be inverses. However, it is important to note that the x plus 2 is part of the argument of that logarithm, meaning it's inside of the logarithm, so I can't do 2 minus 2. I cannot further simplify this, right? I would have to do subtraction before I do that exponent since all of this is grouped in the exponent. Not inverses, can't simplify any further. Number 5 are inverses if you check it. All right. To determine if the relation is a function and if it is invertible, for this, remember, if it's 1-to-1, it's invertible, right? When I look at this first graph here, it is a function. Each input maps to one and only one output. Notice I did not just say it passes the vertical line test. Here, it does pass the horizontal line test, which means it's inverse once you reflect across y equals x is also going to pass the vertical line test. Each input maps to one and only one output, and each output is the result or is mapped from only one input. So function and invertible here. Here, not a function, right? I see very clearly using that vertical line test that there are multiple times where one input maps to more than one output. This exponential here is already 1-to-1. It's already invertible. It's already a function. We're good. It's important to notice with this parabola here, I'm going to focus on that one. It is a function. However, it is not invertible, right? This idea, and I'm just going to use these points right here, is that when I reflect across the line y equals x, that negative 1, 2 becomes 2, negative 1. And this, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9, 2 becomes 2, negative 9. And let's just see. So I can get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, so negative 5, negative 6 becomes negative 6, negative 5. And so this would be a sideways parabola. We can very clearly see not a function, right? So it is currently not invertible. However, if I take out the left-hand side of this, go boop, and start it at the vertex. So using a domain of just negative 5 to infinity, right? So from here on to the right, then now it's a one-to-one function and invertible. And so we would actually end up with only this function right here. Notice that would now be a function. Okay. Please be careful. One of the most common mistakes is students like to go past that vertex right there, that starting point. Don't do it. Just don't do it. Remember one of the conversations we had in class for this spicy section, odd degree polynomials, especially if there's no, as long as it's not a complicated one, there's only transformations like a reflection here, dilation by 2 here. So then odd degree are going to be one-to-one and thus invertible. Whereas these evens are going to look like parabolas, and they are not invertible unless we restrict the domain. So restrict the domain to 0 to infinity for both of these. If you graph them, you can see why. Now, this sine function, this is not something we got a chance to discuss, but once again, the idea is just, hey, as long as I can make the function one-to-one, it's invertible. And so a common thing to do is, or there's actually lots of options in this case, because if I take out all of this and all of this, that's now a one-to-one function. I only go from here to here, passes the vertical and horizontal line test. I made it so it's easy to see this domain, but what's actually most common with the sine function is to get rid of this. I'm not going to stress about it. As long as you know how to restrict a domain so that the function's one-to-one, I'm good. So the domain of this restricted function would be negative one-to-one. And so that's important to notice. And then the range of this would be what, negative 3 to 3. And so don't forget that means that the inverse will have a domain of negative 3 to 3 and a range of negative 1 to 1. Talked about this in class today. At the end of the day, don't forget, like, if I'm going to graph a function that's pretty straightforward, a simple one, right? If I have something like that, right? It's fifth degree. That's complicated. It's got 5 zeros. In that case, I'm not just going to use a table. I'm going to use my zeros. I'm going to use my factors. I'm going to figure all that stuff out. But if I have something straightforward and simple, like g of x here, then I know there's no horizontal translation. So I'm just going to start at 0. And we want to remember that x's are inputs. You substitute them in, you get stuff out. I did this earlier in class. That's the only reason I know all these off the top of my head. And still, I'm having to think about it. And so if that's g of x, the inverse of g of x, right, would be negative 10, negative 2, negative 3, negative 1, negative 2, 0, negative 1, 1, 6, 2. And so just graph those points. If you want to have extra evidence of understanding, graph g of x, graph the inverse of g of x, and graph the reflection. But you didn't need all that. Here with h of x, one thing, there's a reason why this is in the medium section. the thing we'd want to notice is one, it's a parabola. We should know the vertex would be 3, 0. Because a times x minus h squared plus k. And so I would start at that 3, 0. I'm not going to start with or have a middle of 0. I'm going to start at that vertex. And in general, that's what you're going to want to do with functions like this is find that key point based on transformations, kind of start at 0, 0, and if there's horizontal translation, that h, take care of that. Okay, substituting these numbers in, I get this. Sorry, I'm on the struggle bus right now. There we go. What we'd want to notice though is this is not a one-to-one function. You could graph it, but you would see it again. So I'm going to take that out. 1, 2, 3. Ooh, that's, yeah, I'll just go ahead and graph this. 1, 2, 3, 4, 2, and 5, 8. And so notice that's only half of a parabola. I'm going to make my life easier. Yep. So 1. I'm going to go by 2's in the x just to spread it out a little bit. But I'm going by 1's in the y. There we go. Okay. And so its inverse is this function, which I guess now it doesn't make as much sense to have changed that scale. So I'm going to go back to what it was. The reason I say that is I'm not going to change the scale in the x. That would look funky. All right, so 3, 0, 4, 2, 5, 8. And then inverse of h of x would be 0, 3, 2, 4, and 8, 5. And when I look at that, it hopefully makes sense. Because there is my line y equals x, and they are a reflection across that line. Same exact thing with that last one down there. And you'll notice I restricted the domain with that last one. So determine the equation of the inverse of each function, then restrict the domain, et cetera, et cetera. Whew, there's a lot going on in this one, right? This is the last one, hopefully. Good, because I got to go do some more school stuff. Hopefully, this video is helpful. If I can get what? Oh. Thank you. Hopefully it's helpful for those who need it. So an example with number 1, if I want my inverse function, I'm going to start using my inverses so that I can get my input to become my output. And I'm going to write my final answer here in a couple of different methods so that you can see all the possible options. So notice I'm just using the cube root of a cube. And so what I get is x equals the cube root of y plus 2. And so this is honestly the most precise understanding. That's what we'd also call g of y. But you can also rewrite this, we would call that f of y. Yeah, because it's not the g function anymore. But you can also say the inverse of g of x. And this is the more traditional way to write that function. Notice I've just made that y become an x again. And so there you go. If you're trying to, so let's look at the original function here. If I'm looking at the domain for number 1, I would actually just refer you back up to here. That's the same exact function. I use that intentionally so that you could go back and look at it or just use a graphing calculator. And so when I'm looking at the domain there for that original, it never quits going left, never quits going right. Notice minimum x, maximum x. That's it. Range. It never quits going down, so minimum y is negative infinity. Maximum y is positive infinity. There's my domain and range. I asked you for the intercept, so don't forget. Honestly, if I want an x-intercept, I know that my input or my x is 0, or my y is 0, my bad. And so what I might do is, especially because I have the inverse function right here, I might just substitute 0 into this to get my x-intercept. And that makes things easy because I got 0 plus 2 is 2, and so I've got the cube root of 2, and the y is 0. You would get exactly the same thing if you substitute 0 in for g of x at the very beginning. Y-intercept, much easier number to deal with, of 0, negative 2. Right, substitute 0 in for x. And then what do I still need? In behavior. So I'm going to go up and look. I got my left-hand side, and so I want to notice in this original function on the left-hand side, as x goes to the left, y is going down. So as x approaches negative infinity, y approaches negative infinity. On the right-hand side, it was going up and to the right. So as x approaches positive infinity, y approaches positive infinity. Whew, there's a whole lot going on there. However, now that I've done all that, the inverse features would be exactly or super easy because my domain is what the range was, right? What was my output is now my input. So negative infinity to infinity. Range, what was my input now becomes my output because those inputs and outputs are transposing. My x-intercept would be what the y-intercept was, except notice negative 2, 0, because the input and output transposed. Y-intercept would be 0, comma, the cube root of 2. And in behavior, it stays exactly the same. I'm going to make sure that's the left-hand side, and here's the right-hand side. And you can go back up and check these features for that inverse function. In fact, I would if I were you. So those features are there for the inverse of g of x. Okay. In a lot of ways, number 2 is exactly the same. I'll just work through finding the inverse function. So notice -4, -4. So y minus 4 is equal to x minus 3 cubed. And the cube root. One thing I do want to remind you and point out here is I do not have to put a cube root or positive negative with a cube root because if I think about, let me finish this. Sorry. Which equals, we'll say g of y. Or you can say the inverse of f of x is equal to the cube root of y minus 4 plus 3. Okay. What I was saying is if you think about what squared is 4, well, 2 squared is 4 and negative 2 squared is 4. But if you think about a cube, 2 cubed is positive 8 and negative 2 cubed is a negative 8. So because there's an odd number of negatives, it would change signs. So the square root, fourth root, sixth root, all those things have the positive and negative that you have to worry about. Don't have to do that with cube roots. In the future, I'm definitely going to change number 3, so I'm not going to do that one right now. But number 4, I will work through that one. The first thing I would want to notice is there's a few ways to actually do this, but the easiest is to undo the multiplication, right? It's x minus 3, following the order of operations, the parentheses. Then x minus 3 is squared, the exponent, and then multiply by 4. So I take a fourth of that, or I divide by 4. So y divided by 4, or 1/4 of y, is equal to x minus 3 squared, square root And so this is technically where it's the positive negative square root of y divided by 4, except we want a function, so we restrict the domain of the original, right? The original function would have looked something like this in concave up, but we're going to restrict that domain to 3 to infinity. So we would only have the positive square root. And so I'm actually going to do a lot of the features under number 3, but that's not where that goes. I can call it q of y then is equal to the square root of y divided by 4 plus 3, or the inverse of p of x is the square root of x divided by 4 plus 3. Whew. So features of my original function, domain, we had to restrict it to 3 to infinity. The range went from the minimum y of 0 to infinity. So there's domain and range. X-intercepts, I've got 1 at 3, 0. Y-intercept, I don't have 1. And what else do I need? Domain, range, intercepts, and behavior. So on the left-hand side, we need to notice on the left-hand side, we got to stop at that vertex. So x is approaching 3. Y is approaching the 0 of that point. On that right-hand side, as x approaches infinity, so as we go to the right, y goes towards infinity, going up. And so now I move to the inverse of p of x. Inputs and outputs transpose, so domain and range should switch. Domain would be 0 to infinity. Range would be 3 to infinity. And if you graph this function, I'm just going to start here and go up that way. That's the reflection across line y equals x. That's what you get when you transpose. Inputs and outputs. X-intercepts, notice there are now none, but there is a y-intercept because that 3, 0 became 0, 3. And finally, for my end behavior, as x goes towards 0 now, y goes towards 3. Notice the x and y switched. On the right-hand side, it was already x goes to infinity, y goes to infinity. All right. And that's that there. Whew. On the last one here, this is more to help you practice solving for an inverse equation. But so I'm not going to do the features. We're going to do a whole lot with logarithms and exponential features in the upcoming unit or final mini unit. For this one, we just need to notice it's x plus 3 that's grouped together. So the last operation-ish is that idea of creating an exponential. So I'm going to use a logarithm. And I've got to use base 2 because that's the base of the exponential. And so log base 2 of y is equal to x plus 3 minus 3 minus 3. X is equal to log base 2 of y minus 3. Now I want to point out, and I want you to be careful, that minus 3 is not inside the logarithm, right? It's only the log base 2 of y. And whatever log base 2 of y is, I subtract 3 from it. So that is why I didn't put parentheses there. In my second one over here, I would want to notice it's x minus 3, then it's the logarithm of that. And at the end of everything, it's plus 4. So minus 4, minus 4. We've worked on this a few times in class now. When you notice, hey, I have a logarithm, so I'm going to do an exponential. It needs to be a base 2 raised to that logarithm. This is also called an anti-log. I've seen it called that before. I think it's more of an archaic term. I haven't seen modern textbooks use that. But we're just making an exponential expression to cancel out that logarithm. and x is equal to 2 to the y minus 4 plus 3. Or I'll just jump straight to this one. The inverse of m of x is equal to 2 to the y minus 4 plus 3. And I want to point out that this should make a lot of sense, and I could have talked about this earlier, but the idea is the inverse of a logarithm is an exponential. The inverse of adding 4 is subtracting 4, and that was the last thing being done, so that's actually now the first thing being done. Then the exponential. And then the first thing being done to that x was minus 3, and the inverse of minus is addition. And notice that's now the last operation being done. So everything is in the inverse order. So hope that was helpful. I know it was a little bit longer than I intended, and I don't have as much time as I wanted to get some more stuff done, but for the sake of helping students, I guess it was worth it. And I say I guess. It was definitely worth it. I hope you have a great weekend studying, and I hope that you get to crush it on the test on Monday.